So now let's look at the relationship between precision and using actual measuring devices. So here we have a ruler, and if we notice, it's marked off by centimeters, so 1 centimeter, 2 centimeters, and they also give us 0.5, so this would be 0.5, 1.5, 2.5 centimeters, and so on. So if I ask you to measure an object, so let's put an object here, we'll put a line. We'll start at the beginning of the ruler. Go to about here. And I ask you, well, what is the length of this line? So you could say, well, it's above 3, and it's just past 3.5 centimeters, but it's not quite at 4. So what do we know from our measuring device? Well, we know that the line is about 3.5 centimeters long, but it's actually a little bit longer than that. So we can estimate what this little extra is. So we'll look closely and we'll say, well, maybe that's about 3.54 centimeters. Now we did take a guess. We estimated, because our measuring device only allowed us to measure up to 3.5, it's a little bit over 3.5, so we're going to say 3.54, and therefore this last digit is always estimated in any measurement. So this is always an estimated value. Okay. So this value is estimated. So let's look at this again using a different measuring device. So here we have a graduated cylinder to measure the volume of a liquid. And remember, for any liquid, any volume, or when we're measuring water, we always measure to what is called the meniscus, this low part here of the line. So you can see that the water is curved here. We're always going to measure to that low point. So we want to figure out what the volume is of this liquid. So we'll see, well, we have 50 milliliters, and this would be 51, 52, 53, 54, and if we're measuring to the bottom of the meniscus, which is actually right here in this case, it is just under 53 milliliters. So if it's just under 53 milliliters, we're going to put our measurement is actually 52 milliliters, but it's more than that. It's almost 53. So I'm going to estimate a final number. I'm going to estimate that number, and I'm going to say, well, it's really close to 53, so it's probably 52.9 milliliters. Again, this is an estimated value. This last number at the end is always estimated. The measuring device didn't tell us that. We had to take our best guess. And this last number limits our precision. So we'll look at one more type of measurement. So we've looked at length, we've looked at volume. So let's look at a mass measurement. And what I'm going to show you is a balance. This is a high precision analytical balance, and they're measuring some blue liquid in here, and we get this mass, 126.8713 grams. Now, even though this is a digital display, it's a digital balance, it still has an estimated value. The estimated value is the last number, this 3. So the scale can measure for sure. It knows these values for sure up to the thousandths place. The 10,000ths place, the scale sees that's a little bit over 0.871, so it estimates a 3 here. Now, what does this do? What does this mean for us in terms of our math, in terms of our numbers? Well, we have something called significant figures. We call a number significant if it falls under one of these several rules. So number 1, all non-zero numbers are significant. So let's look at an example. If I have the number 3.57 and I want to figure out how many significant figures this has, well, I follow rule number 1. I have a 3, a 5, and a 7. All of these numbers are significant because none of them are 0. So if you need to know how many significant figures are in this number, the answer is there are 3 significant figures. Rule number 2. Zeros that are between, or in other words, sandwiched, two non-zero numbers are significant. An example, if I have the number 2067 and I need to know how many numbers are significant in this number, I count 1, 2, 3 numbers that are not 0, and then when I look at the 0 here, it's between two numbers that are not 0. So according to rule number 2, it is significant. So this number has 4 significant figures, or sig figs for short. Rule number 3 is zeros that appear before any non-zero number are not significant, meaning they are not part of the numbers that were measured. These are also known as leading zeros, and these are not significant. And an example, 0.0053. In this example, the 5 and the 3 are not zeros, so they are significant, but the zeros in front, these are just placeholder values. They weren't actually measured. They come before any non-zero number, so according to rule number 3, they are not significant. So in this case, our number only has 2 significant figures. Our fourth and final rule deals with zeros at the end of a number. Zeros that come after non-zero numbers are significant only if there is a decimal point in the number. For example, if I have the number 200 and that does not have any decimal point in it, those zeros are at the end of a number, and there is no decimal point, that will mean this only has one significant figure. But if I give a second example of the same number 200, but with a decimal point, this number, because there is a decimal, those zeros at the end of the number count, so I get the number 3 significant figures. If I do one more example here, 3.400, this number also has 4 significant figures because these zeros come after non-zero numbers, so they're not sandwiched, they're not leading, but there is a decimal point, so they do count. So every number here counts as a significant figure.